is really the same thing as regularization, except we're going to stick something on the end of it. We're going to stick a sigmoid onto the end of a linear regression model and train that and use a different loss function. And all of a sudden, we're building a classifier, a binary classifier. So in this particular case, we're doing just binary classification. So we'll start out with a simple single hidden layer, which is our logistic regression model, basically. So let's try that out. Okay, so once again, I got my standard support code here, and I've got a method that's going to show the feature space. I'm going to take this data, which actually, so this is the wine data set, yet another well-known toy data set. And scikit-learn has a function that'll pull this in for us. And I do my usual, I create a data frame out of it, and the target is the class of wine. But what I'm doing is I'm stripping out anything that is not in class 0 or class 1. So it's actually a 3-class problem. I'm converting it to a 2-class problem just so we have a data set, and because we're doing binary classification. So I'm going to be predicting the class, the kind of wine based upon proline and alcohol, whatever proline is. I definitely know what alcohol is. So our subset data set looks like this. And there's a bunch of class 1s in there as well. But so these are all just binary 0 or 1s. All right, so then these support functions here are just going to show feature space and then also our prediction space. So you can look at those in detail if you like, but you'll just see how they look when we call them and just assume that they're these magic functions. Okay, let's start again. Okay, so I'm loading the data. All right, so the show function takes this subset data frame, and this, of course, is, you can ignore this. This just writes it to a local file on the desktop. So this is 2-dimensional feature space, alcohol and proline, and each point represents an instance, a record from this data frame. I'm marking its target with a different marker, but this is just a feature space, and creating a classifier is a matter of creating a decision boundary between these things, or they don't have to be contiguous. We could tessellate this space by breaking this up into a little spot here and a little spot here and then a big chunk over here or whatever. There's many ways to do that. Depending on the model, you would get a different split of these records. Okay, so I have a built-in parameter that I made on that function that will also show you the normalized space. Once again, all I did was take the average, which appears to be about 1,000, subtract that from all the values, divide by the standard deviation, and that gets me these standard scores here. Okay, so there's no machine learning involved there. That is just sniffing the data. I always like to see what I'm looking at. And if I looked at this, I go, oh, well, this doesn't seem like it's too hard, especially if I'm willing to allow a little bit of an error. I would just make a decision boundary like this. Okay. So pulling this normalization functionality out, I take my 2 columns and my target, and then I do my normalization. And then I'm just going to call them x underscore and y underscore so I can keep these originals around. All right, let's look at the difference between regression and classification. So now we're experts on regression. How does it look when we want to build a model for classification? Well, as I said, we're just sticking this sigmoid on the end. That's all we're doing. And this is exactly a logistic regression model. Now, how do we change the training loop? It's exactly the same. So remember, I've got this optimizer that I tend to always use, Atom. And then here's the standard thing that I've tattooed on my left forearm. And I just always use it. I don't have to think about it ever again. As long as I create a loss variable, then this little snippet of code is always going to work. The difference is, instead of using an MSE for a loss function, I'm using this binary cross entropy, which is same thing as log loss. And this F is just this function package in PyTorch. Just getting access to some functions. And okay, so that's the only difference. I have a slightly different model in that I'm effectively thresholding the regression output. So it's between 0 and 1, and I get the probability that y equals 1 given x. And I have to change how I measure the loss. And the loss is not measuring accuracy because that's really imprecise. What we want is a penalty, as we saw in the slides. We want a penalty that really smacks us on the nose if we're very confident in the wrong answer. If we're very confident in the right answer, that's cool. But it's mainly about, we don't get a huge boost for that. What we get is a penalty very strongly if we're confident in the wrong answer. And so that's what this loss function does. And the details of it, we'll look at the math we saw briefly, but it's not critical. Just know that that's what it's doing. It's penalizing confident wrong answers. Okay, and it's also smooth. It lets us nicely find this thing. Other than that, that's absolutely it. That's it. So as you'd expect in the code, all you're going to see is this, and everything else is identical. And now I'm printing out a different kind of loss instead of MSE, but other than that, it's absolutely identical. Okay, so let's run it. So let's do a standard logistic regression model. A logistic regression model has 2 betas and the beta 0, but that's implied here. It's got 2 betas on proline for these 2 features, proline and alcohol. And then I'm just going to run it through a sigmoid. So this is the neural net equivalent of logistic regression. And I'm going to use this C-train for classification training. So I'm going to pass in my normalized X, normalized Y, and I played around and I got a learning rate, and I'm going to do a lot of epochs. Okay. So that's my model. Let me make sure I get this in here. Execute. And the log loss starts out pretty high. I'm getting it pretty low. I'm not computing the accuracy, so I can't tell without more information, how good that is. But if we look at this other function I've got, instead of show, it's dshow. This is the decision boundary. First thing we notice is, as we'd expect, the decision boundary is in fact close to a line, but it's actually shaded, right? So there's a threshold that occurs at these black dots. Everything to the right is going to be class 0. Everything to the left is class 1. But as you're near the boundary, it's uncertain. The probabilities are, a shade of one or the other until you get, far over here. Okay, so this is just a handy little function. And all it's doing is at every dot, it's computing the loss, the log loss. And then using a color map, it's saying what's the color of it. And so the loss function, as it nears the center of this, based upon the model that was trained right here, it's going to know that here is roughly a 0.5. That's just based on this loss function that we computed and this model. Okay, so I'm not drawing a line here, just to be clear. I'm saying for every single dot you see here, what is the loss function? And if it's within a small bit, a small tolerance of 0.5, then make a black dot. That's all I'm doing. Okay, so I'm just showing you that in fact, a logistic regression does give you this line, even if you try all combinations of these parameters.
Terence?
Yeah, or features.
Can I ask you a question on the decision boundary?
Yep.
So did you get the decision boundary of 0.5? Is that because of the threshold of a logistic is usually at 0.5?
Well, I just decided that that's what I wanted. Now, in certain cases, I might decide that a false positive was much worse than a false negative, and so I can change that threshold, but that's up to me. And we'll talk about this more when we look at different curves for errors. I simply decided that if there's a 50% chance, if there's a greater than 50% chance that it's class 1, I'd do that. If it's less than, I say it's something else. So I just arbitrarily chose that. I could have chosen something else. But that's a typical, in the absence of any other knowledge about the application, I'll just give them equal weights, false positive, false negative, that kind of stuff.
And then you can adjust that decision boundary somehow with?
Yeah, and I did that in my, Yeah.
Like for some reason, I tried changing the decision at 0.5 to like 1, and then all of a sudden, like,
Yeah, it should be like all the way over there. Let's try
yeah,
0.3 and just see what happens. I have no idea. I'm trying to think on the fly here. It seems like it should. Uh, did I? Well, let's rerun everything just to make sure. It's got to change something. I'd be surprised. I must be.
yeah, yeah. I think you're overriding it with the 0.02.
Yeah, I was just going to say I must be. I must be doing something here. Uh, anyway, I'll have to look at this later, but that is typically what you'd see, right? Mathematically, if you go, well, what's the probability that it's a cat? Well, if it's greater than 50, then you go, okay, it's a cat. If it's less than 50, you say, no, it's a dog. So but that's arbitrary. In a medical situation, you might decide that a false negative on cancer is really, really bad. And so you would adjust that threshold. And that's something we will definitely do when we talk about the area under curves and stuff like that for errors.
Thank you.
Okay, so let's put this back where it was. I must be doing something. I must be checking that else somewhere. It's bugging me now. Where is that data? Okay, grid boundary. That's decisions. Anyway, I'll look at that later. Okay. So that is assuming a particular threshold. Yes. So let's now give it some more power. So instead of a model where we're just doing simple logistic, let's give it, let's see, what did I do to it? I gave it an extra layer and I gave it more neurons. So I gave it 3 neurons instead of 1, and I gave it an extra layer. But I'm using, in this particular case, I could use a ReLU, I'm using sigma. So all I did was change the model, and then it looks like I changed the learning rate a little bit. And so when I run this thing, it'll be slightly different this time when I run it. Notice that I'm getting the loss down from, instead of 0.07, my log loss is 0.04, so it's lower. And look at this beautiful little curve now. And again, I'm not drawing an ellipse or, I mean, like a, a spline or anything like that. I'm literally computing the output, the sigmoid, basically, the output of this model. And if it's close to 0.5, I'm giving it a black dot. So you can see I'm getting a much more complicated surface here, boundary decision, than I can get with a logistic model, which must give a separating hyperplane. That's all it can do. So here I can do nice curves. And so this looks like this one might have actually gotten a better accuracy because this one's on this side of the line, whereas now I've got 2 blues over here. Why is my log loss lower? Well, what does a log loss show? It penalizes if you're confident in a wrong answer. So there might be, look at some of these. These are wrong. And it looks like it's starting to get confident in me. So it's going to get a little higher. So it's not the same thing as accuracy. You might want to look at that. I tend to look at lots of metrics because it's really easy to get fooled by metrics and loss functions. So you want to see lots of them. Anyway, not sure what I put down for this. Yeah, well, anyway, it's definitely able to drive that loss lower because it's a more sophisticated or more complicated model. All right, well, let's crank it up more. So now let's see, I had 2 input variables, 3 neurons. Let's try 2 input variables and 10 neurons. Otherwise, exactly the same. Okay, actually it looks pretty close, but it looks like it curves in a little bit. And it seems to have driven the log loss a little bit lower, but it doesn't look materially different. Let's try it again. Okay, now, because of the randomness of how I started, look at this. This model decided, because it had more power, it said, well, what if I just kind of carve this blue out because it's supposed to be blue? And what if I carve this blue out because it's supposed to be blue? So look at that. I got it down to almost perfection. And the accuracy would be maybe 100% here. Although I could argue that this is probably overfit, jumping into this unnatural zone here. This is probably an outlier that I wouldn't necessarily want to train my model on. But you can see that if I give it just a little more power, wow, you can get a really complicated decision boundary. So let's try something else here. So let's add another layer with 10 neurons. And let's flip the ReLUs. First, let's flip to ReLUs and see what happens. All right, I'm just going to change this to ReLU. Okay, let's train it. Okay, it's not going as low. And I get a very different looking surface. You know what? This one actually looks pretty good to me. I'm not, do we really know this is red down here? Maybe not. Maybe this mass, maybe it should look like this and like this. I don't know. But anyway, that's the training I got, and it didn't go that low. Let's boost it a little bit and see what happens. Okay, now look at that. Now I'm like really low. Okay, so I dropped it all the way to perfection, but look what it had to do. Notice it got a disjoint tessellation of this space. Logistic regression has to be contiguous regions of, cat and dog. This got an island of, class 0 in the middle of class 1. Now, is that a good model? Probably not, right? But you can get a very sophisticated decision breakup of the search space with a complicated model. And if I want, I can toss in more of these things, like let's throw in another layer of 10 just for fun and see what that does. Oh, wow, look at it, it dropped it really fast. So it's a much more powerful model. And so it didn't need very long before it had driven that to 0. Let's see what it does, what it looks like. Oh, that's interesting. Okay. Curves it in here. Anyway, so clearly I'm giving it, more power than it needs. But this is how you learn to get a feel for what your architecture should look like. And, what nonlinearity to use. Like, I'm going to try something here. Let's try this. I'm going to take two vector from the input, make 10 neurons to make a 10 vector. Then I'm going to squish it and see if it'll squish it down to some really good features. And then the last layer will take 3 features and go to 1. I don't know what this is going to do. It's not driving it much lower, but I'm curious to see what it looks like. Interesting. So probably I would almost say that my learning rate is too high because it's going boing, 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 boing. Let's go back to 1 and see what happens. If it oscillates around that loss, it doesn't get any lower, but it's non-zero, it could mean that you're bouncing back and forth in the valley. So you notice I lowered the learning rate and yet I get a better training. Okay, so that's the non-intuitive bit there. Oh, wow, look at this. Somehow there's an X down here, I guess, and it made this a red zone. So you can see that this architecture and this learning rate and the number of these iterations, really matters. Like if I drop this to 5,000, it should be less tight. Yeah, so it got a different model because I stopped it early. And this one makes a little more sense. So I used the poor person's regularization, stopping early. That's what they call it. Okay, questions?
Do you have any time to go over like how exactly you can get like a curved boundary, or how exactly it knows
How it knows what? I'm sorry?
how exactly it knows the curved boundary, or
How do I plot it, or how does it make this?
like how does it make it or plot it?
Oh, okay. The plotting is all done in this function here. And so what I've created here, I know there are functions to do this, but I do it the simplest way. I say, all right, figure out what the space is of variable number 1 and variable number 2, and then make a grid. And that grid is all of these dots you see here, red and blue. All of those dots, that's a grid based upon the min and max of proline and alcohol. And so then what I do is, so once I get this grid of two-dimensional grid of points, I ask the model to compute its sigmoid for every single one of those XY locations. And so that gets a probability between 0 and 1 for every single location here. And then I just make it into a column. It probably comes out as a two-dimensional vector, and I want it just one, so I just do a little reshape. You got to futz with these to make sure you get the shape you want, but whatever. So these are the I'm reshaping because yeah, I want it to be one-dimensional. I take that two-dimensional grid of the answers and I stretch it all the way out so that I can then okay, which direction? I have to think about this. Why? So this is this gives me a Boolean, whether it's close to that boundary or not. And the decisions, why is it reshaped in this direction? And then I use it on the grid again. Oh, this is giving me the coordinates in a list. Okay. Right. So it's already stored as one big long thing, kind of like we do with images. Okay. So anyway, I wrote this, like a month or so ago. So I'm trying to figure out the details, but that's basically what I'm doing is I'm going to every single grid coordinate. I'm saying, what's your loss? I'm sorry, what's your probability? And then I say, if you're greater than, you're going to be, well, actually, I just use that probability in a color map to grade from blue to red. And then when I want to figure out what this boundary is, I get a true or false answer as to whether I want to draw a black dot. And the way I figure that out is I say, is the probability that came out of your model, your sigmoid, 0.5 or really close? And if it is, then I make a black dot at that location, that alcohol and proline feature location.
Great, thank you.
Yep. Sorry, yeah, if you're digging that code, you'll figure it out, but it's been a month. And all of these functions I have are really similar, so. Another question. Yannet, should we try to sit here and act as lab instructors and let the students go through these, or should I move on to multi-class classifiers?
Do you have an example in which you put the accuracy of the, again, like what you guys need to do here is to put accuracy like
Yeah, so we can easily
validation loss and then
Yeah.
the validation accuracy you
Okay.
want.
Yeah, all right.
So
Let's
do
copy that back.
you actually have a function Terence that computes accuracy, because that's kind of pretty useful for
Yeah, I'll throw that in too.
this.
So let's just do accuracy then. Let's just do that. Okay, so let's modify our original function.
Yeah, because you were using all these models in terms of the training loss, right?
Yep.
But then they don't know which one of these models is the best, right?
That's right. So we need to go, let's see, torch argmax y thread. And this gives me the y predicted, or the y class, right? Do I need to say like dim equals 1, something like that? That sounds familiar. Let me look. I think in multi-class I did that. Argmax.
Since Terence, since this is binary, probably you just have to put, this is binary classification, right?
Oh, yeah, I'm sorry.
You don't use argmax.
You're absolutely right.
Bigger than.
Yeah. I was thinking multi-class all of a sudden. You're right.
Yeah.
I don't need to do that.
Maybe if you show them how to do it outside of that training loop so that they see the computation, if you have a little piece of, I don't know, whatever you
Yeah, so let's see here. Let me think. So I've got let's see, here's my model. Let's see, let's start with the simplest model. Make sure I reset everybody. Okay, so I'm going to train this model. And now if I run, say, we'll start with a training set just to make sure that, so this should give, yeah. Okay, so there's one problem. I didn't split out my training set, so let's do that. Okay, so where is my X and Y? So that's just showing the data set. Okay. Let's normalize it all together. It's probably cheating a little bit. Let's see, if I add that, that is going to have a ripple effect. All right, well, I'll show you what. I will compute the accuracy, even though it's only going to be on the training set, because otherwise I'm going to have to go through and change my X variables and I'll screw something up here. So let's go back, and this is just my normalized X. Okay, so this gives me probabilities that it's the class 1. So if we say, we convert this 0.5, then this tells us whether it's class 1 or class 2, right? So this is where I'd really be doing my thresholding. So if I wanted 0.3, I could do that as well. And that gives me different answers. But let's say in the absence of any other knowledge, if the probability, so this is probability that y equals 1 given x, if that probability is greater than 0.5, we're going to call it class 1. Otherwise, we're going to call it class 2. Let's see here. Let's see what this looks like. Oh, it's still using vector. I don't know.
Sometimes if you put int on top of this Boolean, it will give you like a 0, 1.
Let's do it as type. Yeah, let's do it as type. How's that? Is that what you're saying?
The thing is that this is an torch object.
Yeah, right. Okay, so that's fine. NumPy.
Okay, yeah, exactly. You will have to like, yeah.
Yay! There we go. Okay. All right. So
there is a way of doing it in Torch too, but I always
I don't know what it is.
Think about.
Okay, so now we have these predictions, and we also know what the true predictions are. The true predictions are just y. Okay, so now we just check. Okay, how are they the same? And we get well, obviously, hey, wait a minute, that should be a vector. That must be checking them all. That's interesting. And what's the type of this thing? Oh, it's a tensor. We want that as NumPy. And by class, then we're comparing NumPy to NumPy, because otherwise we're doing NumPy to tensor. Okay, now we go. So this tells us where they're the same, and we want them to be the same. And then we can just literally sum that up, and that will tell us how many are correct. And that will tell us how many there are. So we got 125 out of 130 correct. So this is n correct equals this. And this is n. So we'll say we are training accuracy. And that is n correct times 100 divided by n. You rascal. Is that flatten? How do I get that damn thing out of there? Remember, it was a, let's see if I say 0. Because number correct came out as an array, right? So actually, I guess I don't need this. Yeah, there we go. Okay, so that's my training accuracy. So you get the output of the model. And remember, that's a sigmoid. So that's going to be a number between 0 and 1. And if it's greater than 0.5, in the absence of any other information, I'm just going to go, well, all right, call that class 1, because that's what that probability represents. And otherwise, it's going to be, if it's 0.5 or below, then it would be class 0. And so these get, that gets a 1 or a 0, because I convert it to n. And I compare that to the 1 or 0s that were in my true, and this is what I predicted. So I check to see if they're equal, and that gives me this vector of true and false, and I want them all to be true, but there's a few false. And so I just sum them up, and that makes false 0 and true 1, and gives me a total. And I ask, okay, well, how many are there in general? And then I just say, how many did I get right? So that's how you compute the accuracy the hard way. Much of the time, a model will just tell you what that is, depending on what library we're using. So if I had a validation,
in all my code, I'll write this type of thing.
Okay, good.
So it'll be useful for you guys to like try to rewrite this notebook so that it shows you accuracy of validation. So that's
Yeah,
actually a
exactly.
good exercise. Yeah.
That's something fun for you to do. Push this back. Okay, any other questions? Let me just give you a little teaser for next time. Because accuracy is a lot more complicated when we have more than one class. So we're going to be using the MNIST data set, and I have a subset just so that we don't blow out our CPUs, and we can train it, simply and quickly. So there's 10,000 in my little subset, and the images are 28 by 28. And if you take a 28 by 28 image and you line it all out flat, you get 784 dots. And each one of those dots is a pixel on the image, and it's represented as a number as to the grayscale value. You can see that some of these are slightly gray, right? And so those 784 pixels represent features of one instance, one image. And so here's a handy little routine I've got called Image Grid that will draw the pixels or the pictures and put the truth next to it. You can see some of these are a little weird. Like somehow that's a 5 for somebody. Um, and once again, I do a random forest baseline, and you can see a random forest does actually a very good job on this. It gets 97% accuracy. Um, and then I'll introduce you to this thing called confusion matrix, where depending on which library you're using, the predicted digit 0 through 9 is here, and the true digit is here. So we want all of these. This is the count that had a predicted 9. I'm sorry, the number was predicted was 9, and in fact, it was a 9. And so you want all of these to be as high as possible, and you want the off diagonals to be 0. So this confusion matrix, by the way, I got this handy little thing. I like to do everything in data frames so I can make it look nice, because I can't tell what these columns and rows are. So then once we have it from a random forest, we'll train a neural net to do this. And then I do this for the validation error, and I compute this, and I compute the accuracy. Oh yeah, torch sum. Anyway, you can see I'm doing the accuracy on this thing here. And then while we're at it, we can do the whole thing where we're training or showing the train and test loss while we're training, and we can look at the way this thing trains. We can play around with the number of neurons, and we can get a variety of different histories. And this will tell us something about how we pick our learning rates and that kind of stuff. So anyway, that's a preview for next time.
Professor, I have another question.
Sure.
So could we conceptualize the decision boundary of a neural network as a combination of individual decision boundaries?
I think so, because in the final layer, what we're doing, let's see here. Let's see if we got a more complicated, where is a picture of a more complicated one. That one's too simple. I thought didn't I have a picture? Oh, we did 3, there we go. Or actually, let's go back to the slide. Let me find out the slides here. So if we look at this model, one way to think about this layer right here, you guys can see my cursor move, right? Yeah, okay, good. So one way to think of this is just regular logistic regression. But I've got the world's best features. How did I figure out what these features are? Well, I didn't use my brain. I just used a kind of a subnetwork beforehand. So I used the, say, proline and alcohol as features, but I ran it through a transformation that created this giant vector in, I don't know, what is it, 10 space. And so each one of these is in fact the output of a predictor.
Do those transformations happen all at once, or would it be sequentially?
All at once, you mean like in parallel?
Yes.
Well, it depends on the underlying implementation and what kind of machine I'm running on. So if I'm in the ideal world, I'm executing the code, it's controlled from the main processor, but it has shipped the problem, the model and my data off to a GPU, which is a parallel processor. And it's going to execute all of this as one giant matrix vector multiply. And in principle, that can all be done in parallel. Even on the main CPU, it can partially be done in parallel, depending on the library and the machine I'm on, things like that. So yeah, that's the advantage. It can all happen just like that. What's that?
Okay. It's definitely easy for me to visualize kind of the decision boundary based on it being like a linear or sigmoid function, but is there a resource, or would it be even helpful to find a resource that would help us visualize how the decision boundary changes when you have more like...
You know, everything I've seen is sort of hand drawn. Oh, it's going to look like this or look like that. Whereas I actually just computed it all by playing around. So all these different surfaces, I just tried different architectures and tried to figure out what it looked like. So obviously for plain logistic, I get a line. If I give it nonlinearity, I get a curvilinear thing. Early on, I had some stuff, and I think actually Yannet has some good slides on this for when she does deep learning. But if you look at this original thing that I was doing here, this is a clear indication that, so remember, 2 linear layers in a row doesn't change the fact that you're getting a line out. If I glue them together, though, with nonlinearities, I get something much more sophisticated. And in my mind, this is 2 lines clipped. So it's kind of what you're getting at. I don't know whether that's true or if it's just a metaphor that works in my brain. But different nonlinearities will give you different, and of course, it depends on how long I trained it and what my parameters were, or my hyperparameters were. But I wouldn't worry. See, the thing is, we're sitting here in 2 space, but we never have 2-dimensional problems. Usually we have hundreds of problems or thousands of features, right? So we're never really able to visualize it anyway. And so I'm not sure it helps that much to think about what that decision surface looks like other than it's linear or nonlinear or, highly nonlinear, something like that. It gets really hard to think about anyway. So the easiest thing, at least for my mind, but I kind of like linear algebra and vectors and stuff. So the easiest thing for me to think of is this thing just transforming vectors. Whoop. What happened? Something like this. So I'm taking this vector, converting it to this space.
Terence, one thing that would be useful is, since you have the code anyways, is to look at the random forest of the same problem, because it's gonna look different. Just to give her another example, like since you can feed the same thing over.
Yeah, if you look at let's get this off. Yeah, and I don't currently have this for a random forest, but I will. I have a guy in Romania that's working with me. Some random dude I met on the internet has been helping me with this code. It's awesome. So if you look at my D-tree thing that's for visualizing individual decision trees of a random forest, there's a part of it that will show you how it breaks up. This is 1-dimensional feature space, and then here's 2-dimensional feature space. And you can see that a random forest, well, at least a decision tree, is getting square. So it's not trying to draw like a curve or like even, a curvilinear thing. It's finding square regions. And I think if you look down from above, it's taking this 2-dimensional feature space. So this would be like proline and alcohol from what we were looking at just now. Looking down on it, you can see that it tessellates this space into square regions. That's just how decision trees work. And so you get a different breakup of this feature space than you do with a neural network. And so every model has a different kind of way of breaking up feature space, at least if we're doing a classification here. And so if I were doing a random forest, I would have multiple of these, and then the boundaries would be fuzzy based upon where these things landed. And eventually I'll do that in my infinite spare time.
Yeah, like I think that decision boundaries give you some intuition, but it's always like 2-dimensional, basically, that you can see something, and after that, it's just very difficult to say more. But it's very interesting to see the difference between, say, a random forest, a tree-based model, and a neural network or a logistic regression, which are going to give you very different decision boundaries.
Yep. So if you wanted to play around a little bit, you can pip install D-tree Viz and try it on that simple model that we had, and it will show you how it breaks up the space versus the sort of curvy thing. That can be
But I think your same code, if you just use your random forest instead of your neural network, is gonna give it to you just numerically, right?
That's true, except yeah, I'm not getting probabilities out of the random forest by default. I guess you could call prob A.
You could call a
Prob A.
probability. Yeah.
But my stupid code doesn't know to call the different functions. So, but I could change it to do that. Yeah, that would be kind of cool.
Yeah, anybody can change it. Probably very simple. Like if they want to see it. You know?
Yep. Okay, so I am guessing that this is a giant fire hose, and unless you're spending a lot of time, you're kind of getting the generalities, but that's fine. I'm open to suggestions for improving things for the next lecture. If you'd like me to, code in front of you instead of stepping through the notebook, whatever you like. But what we need to do next time is I need to get you into multi-class classification, and then how do we use a GPU? Some simple examples, and then we'll kind of be wrapping up for my part of this, and we'll do data loaders. So, we have to use stochastic gradient descent, and then data loaders to help us with this mini batching. And then those are sort of the key. Like if you get that, then I think you'll understand what Yannet's talking about, and she can take you through some more examples that are a little more real. I'm playing with toys, and she's going to show you real stuff. Toy data set. Okay. Well, if there's no questions, comments, or social commentary, we should end for the night. And I look forward to talking to you guys on next Monday, but feel free to send me questions about these notebooks or whatever. All righty.
Thank you.
Catch you all later.
Thank you.
And I'll let you know when the recording is up.
Thank you.
Okay.
Thank you.
Yeah.